Hello, welcome to Advanced Functions, Logarithmic Functions, Lesson 1. So going over the exponent laws, the multiplication law is m to the power of x times m to the power of y, and it can be rewritten as m to the power of x plus y. The division, m to the power of x divided by m to the power of y, is equal to m to the power of x minus y. For the exponent of an exponent, such as m to the power of x in brackets to the power of y, we can rewrite that as m to the power of x times y. For the power of a product, m times n to the power of x, it can be rewritten as m to the power of x times n to the power of x. And for the power of a quotient, m divided by n in brackets to the power of x, can be rewritten as m to the power of x divided by n to the power of x. Next, anything to the power of 0 will all equals 1. And for a negative exponent, such as m to the power of negative x, you can rewrite it as 1 over m to the power of x. And finally, for a fractional exponent, m to the power of x over y, I can rewrite that as the y root of m to the power of x. So for my exponential functions, here's my standard equation, ab to the power of k times x minus d plus c, and a would be my vertical stretch slash compress, and a cannot equal 0 because then the function will just be a constant at the value of c. B is the base of my exponential function, and b must be greater than 0 because you cannot take an exponential function of a negative number or an exponential function of 0, and b cannot equal 1 because that would just be another constant value. K is my horizontal stretch slash compress, and d is my horizontal translation, and c is both my vertical translation and the value of my horizontal asymptote. So here's exponential function examples of the simplest exponential functions. It's just b to the power of x. And for my first one, I did 2 to the power of x. So I essentially just take my x values on the left and sub them into my f of x. So 2 to the power of negative 2 would equal 1 over 4. 2 to the power of negative 1 would equal 1 over 2. 2 to the power of 0 would equal 1 along with every other number. 2 to the power of 1 would equal 2, and 4, and 8, and so on. So on my right side, I have my other function, 1 over 2 to the power of x, and I essentially do the same thing with my x value. I just sub it in for the exponent. So 1 over 2 to the power of negative 2 is 4, 1 over 2 to the power of negative 1 is 2, and then 1, and then 1 over 2, 1 over 4, and 1 over 8, and so on. So graphing my two functions next to each other, you can see that my green function, 2 to the power of x, is my increasing function, and my blue function, 1 over 2 to the power of x, is my decreasing function. So here are some features of y equals b to the power of x. When my base value is greater than 0, my function is increasing, and when my base value is between 0 and 1, my function is decreasing. My vertical asymptote does not exist, and my horizontal asymptote is at y equals 0. My x-intercept does not exist because I have a horizontal asymptote on the x-axis, and my y-intercept will be 1 because anything to the power of 0 is equal to 1. My domain is any real number, and my range is all real numbers, but y must be greater than 0. Okay, so next is inverse functions. Inverse functions are functions that undo the action of another function, and there's many ways to solve for the inverse of a function. So first, if you're given a table, so let's say the table on the left, f of x, is my function, where x equals to 1, 2, 3, and 4, and y equals to 3, 6, 9, and 12. The inverse of this function would just be me switching the x and y values, so my x would now be 3, 6, 9, 12, and my y would be 1, 2, 3, 4. Next, if you're given an equation, y equals x, you have to set that equation to equal x equals y, and then you isolate for y. So what this means is, for my first equation, f of x is y equals 3x plus 4. The inverse of this function would just be me setting x equal to 3y plus 4, and then solving for y. So x minus 4 equals to 3y, and then dividing both sides by 3, I get my inverse function, y equals to x minus 4 divided by 3. So if I'm given a graph, I can reflect my function along the line y equals x. So my black line here is my function, f of x, and that is equal to y equals 4x. My red line is my inverse function, y equals 1 over 4x, and you can see how the two functions are reflected against the blue line, y equals x. Next, let's find the inverse of an exponential function. So we know exponential functions in our most basic form are y equals b to the power of x, and then swapping the x and y, we get x equals b to the power of y. And now to isolate for y, we would need to use a logarithm. We would write y equals log base b of x. So these are logarithmic functions, and the form goes y equals a times log base b of k times x minus d plus c. And a would be my vertical stretch slash compress, and a cannot equal 0 because then my function would just be a constant at c. B is the base of my logarithmic function, and again, it has to be greater than 0 and cannot equal 1. K is my horizontal stretch and compress, and D is my horizontal translation and my vertical asymptote. C is my vertical translation. So let's look at some examples of the simplest logarithmic functions, log base b of x. So my first function, log base 2 of x, My x values are 1 over 4, 1 over 2, 1, 2, 4, and 8. And this time, instead of applying my x to the function, I'm kind of working backwards. I'm asking myself, what exponent does my base have to be put to equal my x value? So what that means is my first base is 2, so I would have to ask myself, what exponent does 2 have to be put to equal 1 over 4? And that would, of course, be 2 to the power of negative 2. And then I would keep going for 1 over 2. 2 to the power of negative 1 would equal 1 over 2. 2 to the power of 0, along with every other number, would equal 1. 2 to the power of 1 is equal to 2. 2 to the power of 2 is equal to 4. And 2 to the power of 3 is equal to 8. And for my right side, I'm doing the same thing I do with my exponential function. I have log base 1 over 2x, and I'm doing the same thing, but just working backwards. So 1 over 2 to the power of 2 would equal 1 over 4. 1 over 2 to the power of 1 would equal 1 over 2. 1 over 2 to the power of 0 would equal 1, and then 2, 4, and 8, and so on. So here are my two functions next to each other. You can see that my black function, log base 2 of x, is my increasing function, and my green function, log base 1 over 2 of x, is my decreasing function. So here are some features of my logarithmic function and the graph. When my base value is greater than 0, my function is increasing. When my base value is between 0 and 1, my function is decreasing. I have a vertical asymptote at x equals 0. I don't have a horizontal asymptote. I have an x-intercept at x equals 1, and I don't have a y-intercept because of my vertical asymptote. I have a domain of all real numbers, but my x value must be greater than 0, and I have a range of all real numbers. So finally, with this comparison of the two functions, you can see how their properties are related. So for both of the functions, when my b value is greater than 0, my function is increasing, and when my b value is between 0 and 1, my function is decreasing. For my exponential function, I don't have a vertical asymptote, but I have a horizontal asymptote at y equals 0. And for my logarithmic function, I have a vertical asymptote at x equals 0, but I don't have a horizontal asymptote. For my exponential function, I don't have an x-intercept, but I have a y-intercept at y equals 1. And for my logarithmic function, I have an x-intercept at x equals 1, but I don't have a y-intercept. And finally, for my exponential function, I have a domain of all real numbers and a range of all real numbers, but y must be greater than 0. And for my logarithmic function, I have a domain of all real numbers, but x must be greater than 0, and a range of all real numbers. So you can see how the inverse of functions swap their domain and range, their x and y-intercepts, and their horizontal and vertical asymptotes. Thanks for watching.